Hi, welcome to Make or Repair. Today I'm going to look at part 2 of the dummy loudspeaker project, where I've already made this loudspeaker and it had a few problems. In particular, the attenuation worked as a dummy load perfectly well, but the attenuation would drift with temperature quite badly. When I switched between 4 and 8 ohms, the attenuation changed and things like that. So to make a dummy loudspeaker, we need nothing more really than a resistor, perhaps 8 ohm, 4 ohm, maybe 2 ohm, just depends what you've got, and enough wattage. Anyway, let's have a look at the old design versus the new design and why I think the new one is going to be a lot better. Both are based on simple voltage divider. The old divider on the left adds up to 8.1 ohms and the new one on the right 8.02 ohms, so both are near enough. The output from the divider is symmetrical about the centre, not just at the bottom, to support push-pull amplifier configurations, and it also gives a differential output. I discussed that more in part 1. But the differential approach is maintained in version 2. So if we don't do this, then we get a very large common mode signal going through into our analyzer or whatever else it is that we're using. Let's compare this then with the new design, and it's still a divider chain, just a bit longer, adding up to 8.02. These 1.8 ohms allow me to take multiple taps from the divider chain. So whereas in the original, we can see the attenuation is 20 log 0.1 over 8.1, which is 38 dBV attenuation, thereabouts. I thought that would be okay, but it turned out to be a bit excessive. The new one, in its multiple taps, it has 0 dB in one position. And then the next position is 5.18 dB, so roughly 5, and then 19.81, so roughly 20. So I'm pretty happy with those. The problem with a high amount of attenuation is that it will mask the signal to noise ratio. When you're running a high quality amplifier at very high level, you do need quite a lot of attenuation, but yeah, unfortunately, you can't see the signal to noise ratio necessarily with your audio analyzer or whatever it is that you're using. Another particular problem that I faced is that because I used what I got in the drawer, my 0.1 ohm resistor was a completely different type to the 4 ohm resistors, and it isn't mounted on the heatsink. So it has different thermal performance, and what happens as a result of that is the attenuation shifts a lot as the temperature of these resistors goes up, and they do go up an awful lot. Let's have a look at how we get to a 4 ohm loudspeaker though. So here's the 4 ohm design. So on the left hand side we can see the original, and what we've done, there's our chain still all the way down this side, and each 4 ohm resistor has another 4 ohm that can be switched in parallel with it, making them 2 ohms. So of course that becomes a 4.1 ohm chain instead of a 8.1 ohm chain. If we look at the attenuation, we can see that it actually changes. It goes down from about 38 dB down to about 32. So that's unfortunate. The fact it changes attenuation is a bit of a pain when we're using it. It's not a huge problem, but it could be nicer. And the reason that happens is because the divider ratio is changing. Instead of 0.1 over 8.1, it's 0.1 over 4.1 now. So that's the root cause of that. Let's have a look on the right hand side. We can see my very simple solution to that particular problem. And of course I could have retrofitted it in the old design, not a problem. So it's still got the resistance chain, but what we've got over here is a completely separate 8 ohms that goes in parallel. And the end result of that is that although it switches the resistance down to pretty much exactly 4 ohms, as a voltage divider, there is no change in this main 8 ohm string at all. So the attenuation shouldn't shift when we switch between 4 ohms and 8 ohms. That makes it a lot easier to get a single calibration point to feed that into our signal analyzer and be able to analyze our signals. Let's take a look at the very final diagram. So here I'm just looking purely at the new design. There's an optional piece that I'm adding to the right hand side here. Now, I'm not actually going to add that for this video. I will look at adding that later. And basically it's some back-to-back Zeners and a couple of protection resistors. So this is just in case I end up with a kind of like a mains voltage coming through this. This is a last-ditch attempt just to protect the audio signal analyzer from getting fried by that high voltage. I might actually build this as a separate little plug-in that will actually plug onto the front of the analyzer rather than being part of the actual loudspeaker. A few other little notes. The heatsink is twice the size of the version 1. They're going to dissipate a lot of heat, but I'm also going to put 2 fans underneath those to blow air through them, and the whole case itself will be perforated. The resistors are all the same make and thermal style, and they're all chassis mounted onto common heatsinks. So all the thermal performance should all be much more tied together than it is in the current design. Now, I've made some notes up here But I can do a -10 or a -30 dB relatively easy just by changing some of these resistor ratios. I can still keep my total of 8.02 ohms. So for example, I've said that I can use a 0.931 ohm and a 0.866 ohm and things like that to replace one of the 1.8s. And that will give me a -10 dB. So I can play around with those to my heart's content at a later date. But for the moment, I'm going with what I've got, -19.81 dB volts and -5.18 and a 0 dB, of course, as well. Something else to just note on the right hand side here, I only used one BNC connector in the original. What I've done here is I've actually used two BNCs just to highlight that this is actually a differential output, not a single-ended output. One of the things I can do with that then is I can actually tie the ground of the amplifier through to the ground of the signal analyzer if I want to, just using this common line that runs through the center. So let's go and have a look at the build and then we'll test it. With two massive heatsinks, stacks of resistors, two fans to fit inside. The first thing I need is a ventilated box. It needs to be a bit bigger than a shoebox. So off the shelf was way too expensive, so I decided to make my own from perforated aluminium offcut. 5mm holes top and bottom and 3mm for the side. Finally, I'll print some plastic bezel just to make it look a little bit prettier. It is sort of an interlocking U-shapes, and I formed them by riveting and screwing together with aluminium angles. And you could of course bend it from larger sheets, but I decided to go for this method. Just makes life easier. I put some threaded inserts in the bottom to enable it to be fastened or to come apart as needed, and this is because the aluminium's thin and full of holes, so it's hard to get mounting points. The fan is mounted on two brackets to give it a little clearance from the base. I made mine from bent aluminium scraps, but standoffs or printed brackets will be fine. This gap helps airflow and reduces the noise of air passing through the hole edges. Then the fans of course are mounted onto the brackets and using rubber grommets to reduce vibration. The heatsinks are mounted to fully catch all the airflow in the fins and form a slight pyramid shape, so to make the best use of the air. They're about 15mm above the fans. And of course the resistors are distributed across the heatsink so that every 50 watts or thereabouts has roughly the same surface area for dissipation. They are of course pasted and they're fitted using threaded holes. Having got the basic construction finished, I printed a nice template for the front panel, drilled, mounted a fascia laminate, and then I arranged the front panel to be removable so I could fit all the controls, then do all the wiring before reattaching the panel. And this makes access for servicing a lot easier. And lastly, attaching the plastic trim, and we're ready to test. Plug it into the power supply and see how noisy it is. So there is a little bit of fan noise going on. I will just shut up for a second so we can hear how much that is. Alright, let's put the fan of this thing on full then. Yeah, I can definitely hear that. But oh my word, that is throwing some cold air through the top of that, no problem at all. Let me take the resistance measurements across these terminals. Okay, so I am going to use my 6.5 digit Keithley residual amount there. We'll clip it on. Well, anyway, there you go, 0.837, so we're 37 milliohms out, so that's pretty decent. Switch it to 4, and let's see what there. Oh, look at that, that's pretty much bang on, isn't it? 4.007.008, let's call that. So these are close enough to 8 and 4 that when I'm using my signal analyzer, I won't need to compensate for that small amount just there, because you know, it's irrelevant in the scheme of what we're going to be measuring. What we're using it for in the signal analyzer, by the way, is to change the dB volt reading that we take into wattage. Let's try the left channel now. So left in 4 ohms is 4.018. So that's really just the error of that sense resistor in the middle there, the 0.02 error from the sense resistor. And let's switch this to 8 ohms. And look at that, that's pretty good, isn't it? 8.026. So I'm really happy with that. The 4 and 8 ohms are pretty much bang on, irrespective of which side I'm measuring them on. So it's superb. So let's have a look now at actually connecting this to an amplifier and a signal analyzer and use it for its intended purpose. Okay, so here's my setup, and I've got the amplifier on the left, then the dummy load, then my audio analyzer just here, and that's showing on the screen at the back. And of course I will show you that full screen when I'm talking about it. What's going on at the moment is I'm outputting from here a signal. is going through the amplifier and coming back out to the dummy load, which is set to 8 ohms at the moment and 0 attenuation. The signal I'm outputting is 12.4 watts, so not huge, but not silly and small. Because I'm measuring it directly, because I've got 0 dBs on here, I do have a 24 dB attenuator set on here. So why have I set it at 20 dBs? Well, because ultimately I'm aiming at 20 dB of attenuation, so that makes life a bit easy, doesn't it? And also, it's not an inconsequential amount of power. We've got a reasonable amount of power going into this device. Let's have a look what happens. Keep in mind, I've got attenuation switched on here. I'm going to put a 5 dB attenuation on here. Let's have a look and see how much that moved. Well, it moved 5.17 dB volts down. So my 5 is actually 5.17 on my left channel. So that's pretty good, isn't it? Let's switch it to 20. And look at that, 0.33. So that would mean I'd moved 19.67. But we can do something else now. Because we've got our attenuation at the front end, we can actually remove that front end attenuation on our signal analyzer and actually get a tighter value with more precision. So now we can see our 0.35, which actually means that it's 19.65 dB of attenuation. But that's pretty good. That's pretty much on the money. And I will attach a little label on here with the actual values. That what I can do now, of course, is if I go across to the dB volt setting, I can actually put my input gain, which is minus 19.65, into that. I've got my 8 ohm loudspeaker set up. Click OK. OK, and we can see that actually this scale now moves. It's now reading the 20 dB volts, which is the output from the amplifier, just like it was before. It's saying we've got 12.4 watts. It's got a total harmonic distortion that it's measuring quite happily. And we're also measuring a nice signal to noise ratio of 86.8, 86.9 dB volts. So that's really, really nice. On here at the moment, the noise floor of the signal analyzer will be down at minus 140 dB volts. So right down here. So we know we are measuring the noise from the amplifier, not the noise floor of the analyzer itself. So let me just put back on some attenuation, and we'll turn this down to 5. So the noise floor should move up, and it has done. And down to 0, the noise floor should move up again. So that's how we know for certain. You can see that when we switch our attenuation on our dummy load, the noise actually moves, which means we are measuring the signal noise and not the noise floor of this, which is exactly what I was trying to do. So I'm going to now switch to the left-hand channel, and we can see that it is basically the same, just in red. So once again, we've got 20 dB, so that's nice, 12.4 watts, etc, etc. Everything is exactly the same as it was before. And just as an aside, none of these values are changing. On the previous build, these would move just very, very fractionally as the temperature changes, and these haven't moved a jot. So this is very good. Okay, and I'll just repeat the same. So 19.65 was my attenuation on the other one, and let's switch that to different values so we get more precision. And look at that. The right hand channel is also 19.65. Exactly the same attenuation left and right. Exactly what I wanted. Let's go for the 5, see what that gives me, and I need a different setting. And that's 14.83, so that is 5.17 down again, which is exactly the same as the left-hand channel. So on my first build, the channels were a bit different. There was a few half a dB or so difference between the two channels, but on this one, I don't have that problem at all. It doesn't matter whether I'm left or right channel, the attenuation is absolutely identical. Let's actually just switch this. So there is our 20 dB volts, and we'll switch it to 4 ohms. Now that might change a little because the loading is different on the amplifier and it's not really supposed to drive 4 ohms. So it'll drop off a little bit, and I will just adjust that out. So we've got 20 dBs again. So that's minus 3.9, is it? There we go, so there's our 20 dBs input again. We're on 4 ohms now, of course, so let's change that as well, just so we've got a power rating. So now we've got 25 watts nearly. So let's see if our 5 and 20 are still about the same. Oh, I've drifted by 0.01, 0.89. Okay, so 20 dB volts coming in. Let's give our 5 attenuation, see where that leaves us. So that is 5.16. So on the 8 ohm it is 5.17. So basically unchanged. And 20, get some more precision in our reading, 0.36. So our attenuation difference between the 4 and the 8 ohm ranges is only 0.01 dB volts. So essentially ignorable. So that's absolutely fantastic. I think we've ticked all of our boxes. The only one left to check is whether or not this is going to get nice and hot, and whether or not then our attenuation is going to shift a long way because of temperature dependency. It's going to shift a little bit, certainly, but let's have a find out. It's got about 200 watts going in the front into the 8 ohm load. It's been about 10-15 minutes and it's reached 60 degrees and seems to be about stable at that. The fan is on half, so I can't even hear it really. The fan noise you can hear at the moment is actually the power supply that's trying to provide all that power. Okay, so I'm going to disconnect this now, connect it up to the amplifier and just see how much that attenuation of 19.6 has actually moved. So our amplifier is outputting 20.01 into our now hot load. So I need to just adjust that by 0.01. So there's our 20 dB volts. So I'm expecting it to reduce by 19.65. So it has moved by 19.64. So the difference between hot and cold in the attenuation is 0.01 dB volts, as opposed to well over a dB volt on the previous versions. So I think this shows really what a bit of attention to detail can do. This second revision is significantly better than the original. While version 1 was completely adequate, version 2 just outperforms it in every aspect. And it delivers every single improvement I was hoping for, and actually a few more besides. So let's take a look and just compare the features. So our first concern was that version 1, it really did get hot quite quickly. And the new version, well, it gets quite warm, but with the fan in particular, you can leave it on for hours with hundreds of watts going into it, and it will only reach about 50 or 60 degrees centigrade. Another problem was the attenuation changing when I switched between 4 and 8 ohms. That made it difficult to use with the signal analyzer. It was moving 5 or 6 dBs when I switched between loads. And while you perhaps wouldn't do that in the middle of testing, it meant you had to reconfigure the analyzer all the time. In the new version, well, switching between 4 and 8 ohms makes virtually no difference, 0.01 dB volts. What about attenuation drift with temperature? Well, the version 1 was pretty poor. The attenuation shifted a huge amount, 1-2 dBs in certain circumstances, just on 10 minutes of heating up. And you could even see a little bit of drift, just as it was working on normal signals. The new one, well, 0.01 dB volts over 60 degrees centigrade is ignorable. Because of the high attenuation on the original version, it was very easy for the signal to noise ratio of the amplifier under test to vanish down into the noise floor of the analyzer. And you could kind of work around that, but it meant messing around quite a lot. The new one, no, it's just easily available. You can see it, not a problem. Right down to sort of 100 dB signal to noise ratio wouldn't present a problem. And you can always turn the attenuation down a bit if you are losing it. Right, what about left and right impedance matching? Well, on the original it was perfectly adequate, there was nothing wrong with it. The new one is within 10 milliohms, so pretty much spot on. And the actual values themselves are within about 20 milliohms of the target 8 ohms and 4 ohms. So fantastic, really. Left and right attenuation are also really close. They match fantastically. And that's because, of course, I used a computer program to pick the optimal solution. The original had no ground bonding, so you couldn't ground it back to the amplifier. The new one you can, and that continues through to the signal analyzer. Differential connections, well, the original was a differential design, but it only had one BNC output on each channel, and that meant you had to use an adapter cable. The new one, of course, it services 2 BNCs, so you just get direct connection through to your differential audio analyzer. The original didn't have switchable attenuation, wasn't a feature I thought of, but someone pointed it out in the comments, and I decided to implement it. In this design, it was particularly easy. And finally, an actual direct speaker through connection, so you can switch the attenuation out completely and look at the original signal. Perhaps not something I'll use all the time, but actually for calibration and things like that, it was really handy. So I'll take that as a win. So anyway, I think that's it. I really hope you enjoyed this follow-on video. If you did, don't forget to like, comment, share, and subscribe, of course. And I'll see you next time. Bye for now.